Okay, in this lesson, we're going to be talking about our conic section called the hyperbola. We're going to be talking about its definition, its characteristics and components, and some example problems dealing with hyperbola. So let's start off with the definition. Let's start off with the graph. So here's a graph of a horizontal hyperbola. Notice that it's got two pieces. Okay, so it's different from all of our other conic sections in that sense. And the two pieces look kind of like parabolas, although we'll see in a second they've got a distinct difference from parabolas. Okay, they can open left, right, they can open up, down. So let's look at the definition. So a hyperbola is a set of all points in a plane such that the absolute value of the difference of the distances from any point on the hyperbola to two given points is constant. So recall from our study of ellipses that the definition of an ellipse was real similar, the only difference being instead of the difference of a point to the foci was the sum. So any point on the ellipse was the sum of the distances to the focus. Here we've got the difference of the distances, and to make sure that that difference is positive, we take the absolute value of that difference. Okay, so let's look at a given point. Let's say we have, let's pick any, so we can pick any point on the parabola. Let's say this guy right here. So the difference of the distance from that point to one focus minus the distance to the other focus. So if we call this D1 and this D2, then the absolute value of D1 minus D2 is some constant that is the same number for any point along that hyperbola. All right, so that's the definition. Now let's look at some components. Let's get rid of this for space's sake. All right, so transverse axis. Our transverse axis is a segment of length 2a whose endpoints are the vertices of the hyperbola. Okay, so our transverse axis on our graph here would look like so. And if its length is 2a, then half of that would be from the center to one of the two vertices. Okay, next up, let's look at the conjugate axis. The conjugate axis is a segment of length 2b that is perpendicular to the transverse axis. Okay, so perpendicular, going through the center, we don't have endpoints here, but we'll guesstimate something like so. So this is our conjugate axis, and then again, half of that would be b, since the entire axis is 2b. Okay, next up, vertices. The vertices are the endpoints of the transverse axis. Okay, and they are similar to the max or mins of the parabolas of these pieces here that aren't quite parabolas. It's kind of weird to say that since it's opening left and right, but think about them as that turning point there. Okay, the center is the midpoint of the segment connecting the foci of our hyperbola. Okay, so we've got a center point here. Okay, so it's directly in between our two focus points. And our focus point, similar to a parabola, is kind of tucked inside of our two curves. Okay, so it'll be on the other side of the vertex from the center. And all five of these points will always be collinear. Okay, whether they're opening left and right, they'll be collinear on a horizontal line. If they're opening up and down, they'll be collinear on a vertical line. Okay, so next up, slant asymptotes, the lines that the hyperbola approaches but never touches. So in order to find our asymptotes, so here's the key difference between these two pieces and parabolas. We've got asymptotes. In parabolas, we don't. So these, in order to find these, we're going to build kind of a rectangle. So let's see, if we look at If we look at our two vertices here and here, and then we look at the endpoints of our conjugate axis, so if we estimate them being here and here, and then if we were to build a rectangle where each of these points are on each point is on one side of our rectangle, then it would look something like this. Let me make that a little lighter, maybe. Nope. Okay, so if that's our rectangle, then the slant asymptotes are the diagonals or contain the diagonals of this rectangle. So if we were to draw the slant asymptotes, wow, that's big. Let's tone that down a little bit. Okay, so there's one. And then if we were to draw the other, again, it's got to go through the opposite vertices of that rectangle. Okay, so something like so, and it should go through the center. Mine here isn't perfect, but you get the idea. So these would be our slant asymptotes. So our hyperbola would never go on the other side of these slant asymptotes. So they're contained within those. And on an actual graph, if we were to graph the parabolas, then we would use those as guidelines. Okay, what else do we have? The lattice rectum of a hyperbola, real similar to an ellipse. Our lattice rectum, we're going to call the LR, and it's a chord that goes through the focus perpendicular to the transverse axis. Here's our formula for our LR. And on our graph, it's going to look something like so. Perpendicular to our transverse axis, its endpoints are on the hyperbola itself. It goes through a focus. So we'd have another one over here. Okay, eccentricity, similar to an ellipse as well. Eccentricity E is C over A, where C is the distance from focus to center, and A is the distance from the center to focus. So it's going to be a percentage between 0 and 100, or a fraction between 0 and 1, that's going to determine the shape of or the stretch of our hyperbola. So if we, let's maybe go yellow for C, and our C would be from the center to that focus there. That's the distance or the length to the value C. Okay, the general form, not so important to us. What is important to us, though, is this formula here. Now, this is the Pythagorean theorem: a squared plus b squared equals c squared. So if we're given a and b and we want to find c, we can do so this way, or if we're given any two of these variables, we can find the third using this. Notice the difference between this formula and the formula that you were given for ellipses. We're adding, this is a straight up Pythagorean theorem, whereas in an ellipse we were subtracting a squared and b squared. Okay, the reason for that real quick is that if you were to take this c value here, and if you were to move it and turn it, then it would be the hypotenuse here. It would be the same length as if you took the triangle with sides A and B. It would be the hypotenuse there, same length. All right, standard form. So we've got two different directions for hyperbolas. They can open left and right, like we just saw. So we can call those our horizontals. And here's our standard form for horizontals. Looks real similar to ellipses, right? Notice the main difference, the key difference, is the subtraction in between. So now we're subtracting our two fractions instead of adding. All right, we've got our x minus h squared, our y minus k squared over our a squared and b squared, and then our 1 by itself on the right side of the equation. Here's our formulas for finding the vertices, the focus points, and the asymptotes of a horizontal hyperbola. One key thing to note with hyperbolas, another difference from ellipses, is that A does no longer has to be greater than B. Okay, so A no longer has to be greater than B. All right, let's look at our vertical opening hyperbolas. All right, and it's just kind of a real nice rough sketch. We've got a smile and a frown. That's our hyperbola, rough sketch. So notice the difference in our formula. This time we've got y first and x second. So we're subtracting x whenever we have a hyperbola that opens up and down. All right, also note the differences in finding the vertices, foci, and asymptotes. Our plus or minus a switches from our x coordinate to our y. Same thing with our c. All right, so let's use these in a couple of quick problems. Okay, before we do so, if we're ever asked to graph a hyperbola, and you will be asked to graph hyperbolas, here's the 6 main steps that you need to graph a hyperbola. Okay, this is what we'll be looking for when we grade any of these on a quiz or a test. Okay, first thing, plot the center. This is assuming that you are given or have found the equation in standard form. Okay, plot the center first. Next, plot the 2 focus points. Then plot the vertices and the endpoints of the conjugate axis. Okay, once you have both of your axes, you can draw your rectangle. From your rectangle, sketch in your diagonals. I would recommend using a ruler for those. That'll give you a better hyperbola. So sketch in your asymptotes, which will give you guidelines for sketching your hyperbola. Now make sure that you know which quadrants to put your hyperbola in, whether it's opening left, right, or up, down. You can look at your equation for that, or where your vertices and foci are. All right, so example 1. We want to graph the equation x squared over 16 minus y squared over 7 equals 1. First thing I want to do is identify what type of a conic section this is. Okay, I see that I've got my equals 1 on the right side, and then the other important part I see is that I've got this subtraction here. All right, it's in standard form. Because of this subtraction, because of the equals 1, it's got to be a hyperbola. So in order to graph this, I want to go step by step. So let's start with our center. Okay, so since we don't have any parentheses, any h or k values, then they are 0 and 0. So our center is at 0, 0. Our next step is to plot the focus points. Okay, so to find our focus points, we need to determine whether it's going to open left or right or up or down. Okay, since we're subtracting our y coordinates, so our x squared is the positive term, then it's got to be opening left or right. So we're going to get a hyperbola that looks something like this. Okay, so that tells me which formula to use. I want to add my a value to my h value. So if this is a squared, then my a value is 4. So I'm going to have focus points at positive and negative 4, comma 0. I'm going to go ahead and plot those. Actually, what I just plotted was the vertices. Excuse me. So let's go back. So that's the vertices. Let's change that. So do things a little bit out of order. No big deal. All right, so those were our vertices. Now let's find our focus points. Okay, so our foci, whenever you think focus points, think the C value. So if our A value is 4 and our B value is root 7, so we get that from this value here, which is B squared. Then to find our C value, we want to do C squared is, good gracious, let me turn that up, excuse me. Our C value is A squared plus B squared. And then we want to take the square root of that, that's 23. C squared is 23, so if we square root both sides of that, then our C value is plus or minus root 23. Since C is a length, we just want the positive, so let's get rid of that negative there. Okay, so our focus point is going to be plus or minus root 23, comma 0. Okay, so 23 is between, let's see, it's almost 25. So square root of 25 is 5, so root 23 is going to be almost at 5. So there's a focus point there, there's a focus point there. Okay, so now we want to sketch our axes. So we've got our transverse axis is going to go from here to here. Our conjugate axis, remember, is 2b. So b is root 7. See, root 7 is not quite 3, so we're going to go somewhere in between 2 and 3. So there's our conjugate axis. Then I'm going to imagine our rectangle. That goes through the endpoints of both of our axes. So there's our rectangle. Let's maybe make that not so prominent. Okay, and now I want the diagonals that go through there. Okay, so this will give me a good idea as to what my parabola will look like. And I know it's opening left and right. And it's got to touch the vertex. And again, this is just a sketch. And it'll look something like so. Okay, there's our graph. We found our center, focus, foci, vertices. We drew in our axes, our rectangle, diagonals, so that we could draw our hyperbola. All right, let's look at another example. We're asked to graph this equation. Again, note the 1 on the right side. Note the subtraction between. So it's going to be a hyperbola. Also note that the y is first, so this tells us that we're going to have a hyperbola that opens up and down. Okay, so I want to start off with my center. This time our center is not at the origin. Again, we're going to take our center from HK, so our H always goes with our X. So our center is at -2, be careful. Our K is +3. I'm going to go ahead and graph that, -2, 3. So there's the center of our hyperbola. We find our foci next. Again, our foci is our C. We've got our A value, which is 3. Our B value, which is 2. All right, so our A value is 3, B value is 2. So to find our C value, take A squared plus B squared. That's 13. So our C value is the square root of 13. Okay, so since our hyperbola is going to open up and down, then we're going to add and subtract that to our y value. So our focus points are going to be at -2, 3, plus and minus root 13. If you want to write them separately, you're welcome to. So root 13 is bigger than 3 but smaller than 4, so I'm going to go up and plot my point somewhere between 3 and 4. There are my two focus points. Now to find my vertex. My transverse axis endpoints come from my A value. So if we keep our same x value, so all three of these points, since it opens up and down, have the same x value, we're going to take our k value, our y value of our center, and add and subtract our A value. Okay, now we do want to simplify this one. So this guy right here, since we've got a radical, this is in simplest form. But let's go ahead and simplify this. So we get -2, 3 plus 3 is 6. And 3 minus 3 is 0. So here are our two focus points. So -2, 6, or our two vertices, excuse me, -2, 0. Okay, so next up, we want to find the endpoints of our conjugate axis. Our B is 2, so we're going to go out 2 horizontally from our center. Now we're going to sketch our rectangle. Okay, each endpoint of our axes touches or is the midpoint on one side of our rectangle. And then we can kind of sketch in our asymptotes. If you have a ruler, this is where you want to use your ruler. It should go through the center, and it should go through the opposite endpoints of your rectangle. That's beautiful. All right, so we know it opens up or down. It's got to hit our vertices. It's got to stay within those asymptotes. So it should look like so. All right, so there's our hyperbola for example 2. One more quick example. It says find an equation in standard form for the hyperbola that satisfies the given conditions. We're given our two focus points and our transverse axis length. Okay, so again, I like to have a graph going while I'm doing this. So let me pull up a graph real quick. Actually, I'll just sketch a graph for this one. Okay, so if our focus points are at plus or minus 3, 0, so there's 1. There's our other focus point. So our center is halfway in between those. So our center is going to be at the origin. Okay, that's useful to know. So that tells us a couple of things. It tells us that we're going to have just an x squared and a y squared. It also tells us that because of the focus points, it's going to be opening left and right. So it's going to be able to form x squared over a squared minus y squared over b squared, and then 1 on the right side of the equation. Okay, we still got to find our a and our b values though. This, remember our transverse axis is 2a, so if 2a is 4, then that tells us that our a value is 2. If we want a squared, then that means our a squared value is 4, because 2 squared is 4. Now we just got to find our b value. Okay, if we know our a value, we know our c value, because the c value is the distance from the focus to the center. So let's use our Pythagorean theorem. C squared is a squared plus b squared, and plug in what we know. A is 2, 2 squared is 4, c is 3, 3 squared is 9, we want to find b. So b squared is 5. So that makes our b value root 5. But we don't really care about that. We just want b squared. So let's rewrite our equation. We have x squared over 4 minus y squared over 5 equals 1. So let's go back to our problem. Let's make sure we answered it. We were asked to find an equation in standard form, and we did so.